Hey guys, in this episode of our C++ versus Rust series, where we try to implement a NodeGraph, we'll be looking into challenges we will have with thread safety. So where the thread safety challenges occur. Obviously there is some number of connections here that, couple nodes together, So this connection causes that these two nodes need to cooperate in some way. And this connection here causes these two nodes to cooperate and so on. So how do we synchronize this? And this is a big challenge actually. So if it was like a completely random graph where the flow could go any direction, we would probably be better off having one big lock for the whole graph, and just, single threaded. But how about we do it multi-threaded and we try to make it, as awesome as possible? Where do we need locks? Where do we not need locks? And perhaps Rust can help us with the magical Rust, semantics. So what can we do here? We remember that the pins themselves hold a weak reference to the connected pin, right? So we have an aspect of connecting. So if I am disconnecting these two pins, right? So this pin is disconnected from this pin, and it happens dynamically during execution of the graph, right? So graph is doing the execution, for example, processing forwards. What is the state of a graph the moment I'm disconnecting, and what effect does it have on the active processing? So let's say the state of our processing is that some thread is here, so the value reached this input pin of target node U, but some other thread maybe is processing here in this node and it's stuck here. It's some function that takes a lot of time to compute, and we're here, so we have consumed the value from here, and that value is now being processed by this function. When this function finishes, it wants to put the value here on the output pin, right? But when we're disconnecting this pin, what will happen? We would reset this input, we would reset it to default. And when that happens, then this should be also default and should be also default. This value should be dropped, right? So maybe this thread should be aborted, So yeah, these are some considerations to have in our heads. In this episode, we'll only look at the safety issue here. So I don't want to have any pointers that are pointing into wrong places, any data races or anything like that. Well, we will have some data races, I think. We need to think about it. Let's look at this. Let's look first at our current implementation. So this is our fork implementation, and this is not thread safe at all, by no means. And in this implementation, we put data into a ref cell. So the reason we put data in a ref cell, if you look here in the NodeGraph, it's immutable. Those methods are not mutable. None of the methods in this implementation are mutable. Okay, so we're processing the graph. We know that data will change inside of the pins, but those methods are immutable. Same try connect. So when we connect a pin to something, well, this is not a mutable object that we're changing, right? So it's kind of counterintuitive, right? We're adding a connection and it's not a mutable pin we're changing. So we can think about it, but because we use ref cell allows us to mutate the value, even though the owning type is not mutable. So that's why you will see ref cell. Now, if you look at the pin, you have ref cell of option of weak pin, okay, weak output pin in case of input pin, and then you have output pin which has ref cell vec weak graph node input pin. So in this case, the whole vector of pin connections is in a ref cell. So I can just replace the vector, for example, which I'm not doing. I'm just saying ref cell dot borrow mutable and then push, right? So this is what I'm doing. I'm borrow mutable, a ref cell, give me mutable. All right, so this is our implementation that we currently have. So what can we possibly do to make this more thread safe? So one thing we can do, this is one avenue we can go. So you can see that in a previous version we had RC, which is not thread safe. It's just reference counted pointer to this graph node pin. And here we have arc, which means atomic reference count. Arc is not thread safe by any chance. You cannot safely change the arc to different place, but you can safely copy the arc. You can safely clone the arc and get another copy of the same arc. So it will simply atomically, in a thread safe manner, increment reference count, and the object to which it's pointing, all those arcs that you cloned, they point to the same object. So you cannot be changing these objects. They're not pointing to different objects. It's just that you have this thread safety when it comes to cloning. So you can actually use this arc across threads. This RC cannot be used across threads. You cannot clone it in such a way that another thread could use this RC, okay? So this code here is inherently single-threaded. You cannot do anything here on the other thread. So this code allows you to process the graph on multiple threads in some way. So now you can see that the inputs and outputs, they are option vec of arc instead of option vec RC. And then we can see that graph node pin has now data which is RwLock instead of ref cell. So we can see the pattern. We're replacing RC with arc and ref cell with RwLock. Okay, so here we have arc and RwLock, and that makes it thread safe. Here it's single threaded and we have RC and ref cell. They are one-to-one conversion, and we will learn further down that this is actually the case, that these map one-to-one, okay? So let's see at the connect. So in the connect here we have, you see, replace. Replace changes this ref cell, okay? So we're saying that this is the new value here that will be put into the connection, but we need to call replace. So is there something in RwLock we can call to do the same thing? As it turns out, RwLock has a method called write. So you can do write instead of replace. So you can do connection.write, but write in this implementation of RwLock gives you lock result. Okay, that's a result. So unwrapping result like this is kind of lazy coding. I should probably do here something like if okay, else, or question mark, or there should be some error handling done here, okay? Maybe the connect should return an error. Maybe that's the way it should go. Anyway, it's unwrapping at this stage, so maybe we look into error handling in some other episode. And yeah, we just get this result unwrapped, and we get in the result this RwLock, the guard, okay? So the right guard. So the right guard works slightly differently to replace, so you need to deference it with the star in order to get a mutable reference to underlying data. So we want to just assign, you see, output pin me clone. So the me is, of course, the weak reference to the output pin's selfness, and into will convert this into the option, because connection is an option. We need to make it option weak graph node output pin. Okay, so this is a thread safe way of changing the connection. When I'm doing this, there is no other thread that can access this connection at the same time as I'm changing it, okay? Now, why is it important? So regular row pointers, they're atomic on their own usually. You can change them, and one thread will see previous version of a pointer, another thread will see the new version of a pointer, and that's how they work. But you cannot do the same thing with smart pointers. So for example, weak pointer, arc, RC, or any other smart pointers, they cannot be, they're not atomic on their own. As you may remember from my other talk on this channel, there is an atomic smart pointer I have developed in C, and you can use it with kernel. It's developed for Windows kernel use. So it's a specific atomic smart pointer which uses, atomic operations to stay safe. In Rust, there is a construct like this. You would have to put arg into a thing called atomic cell, and it will guarantee you the atomic replacement of the arg, right? We may explore this avenue of putting this weak pointer into atomic cell. So there exists in arg cell package an atomic cell, and there is predefined type aliases, and for example there is something called arg cell and weak cell, and it's nothing else than arg in the atomic cell. And there is also optional arg cell, optional weak cell. So we could actually put all this into optional weak cell. Okay, so that will be the more atomic version of this code. But we get to that in the next episode. In this episode, we will use traditional RwLock from Rust sync. Okay, so what did we do? We secured this pointer with this lock so that we can change it safely, so that, when I acquire the lock, I can replace the pointer and increment the reference count at the same time, and then I can release the lock. So when you're incrementing the reference count, you cannot increment the reference count and at the same time replace the pointer. You need it to be in the atomic operation together, right? So this RwLock guarantees this. Okay, so as we can see, connection write unwrap equals output pin me clone will give us the replacement of the pointer in atomic fashion, right? Then the competing function, right? So the connect is competing with get connection. So what happens is one thread, for example, user interface thread, might be trying to connect two pins because user is clicking mouse and it is a user interface thread, right? And there can be background threads which are rendering the nodes at the moment, processing, and they'll be calling get connection. This is a competing method. This is the race between these two methods, right? So the background threads which process nodes will call get connection, and there is no competition between those threads because they all read, those connections, so they don't change those connections, so they can work together. But the thread that is changing them, which is usually a UI thread, or for example, you are loading the graph from a file, and it can be a background thread that is parsing the file and loading the graph. That will be in conflict with any threads that are trying to process the graph. Okay. So one way of solving it is a global lock, because if we said that threads that process the graph, they don't interfere with each other, whereas threads that are changing the graph, they would, and the one that's changing is user interface. Perhaps it is the case that when user is doing something, we should just block everything because user is doing something. But it's a design decision, right? Right now we're exploring the technical details of the implementation rather than the business use case. You can see that the other methods are implemented in terms of get connection, okay? So you wouldn't expect other methods to deal with this RwLock anymore, because get connection will just give a cloned arg, which means that we have this weak reference because we don't want cycles, okay? We need to upgrade it to an arg, right? And we need to use RwLock to make sure that we're working with this living, output pin, that no one will take it away from us. So yeah, so we use the get connection in, for example, receive data on propagate backwards, right? So here we're gonna get the connection, and this function get connection does the lock and whatsoever, right? So it will do the read lock of this connection, but it will exit the lock the moment when this function exits. So we already have a cloned arg when we're returning, so we are not blocking this, we're not creating any deadlocks here. We just lock this connection variable, which is our RwLock holding this weak pointer. We just lock it to just acquire this, arg, and then we leave the function, so we release the lock. So this is very prompt lock, And before we even do something, before we say node process backwards, we already don't have that lock, okay? We could also look at what get node does. We can see that the node is a weak reference to a node, and get node is just upgrading this weak reference to an arc. There is no lock involved here. And the reason for that is that because we never change this weak reference. This is a const weak reference. So a pin is attached to the node, and the parent node to which it is attached cannot change, right? So we do not need to put that into any lock. However, what is important is that it is still wrapped into a function, into a getNode method, so that whoever wants to get the node will get it through the getNode method, and if a lock is required, we put it just here, right? It will be self-contained lock, and we return the arc anyway. So we can also see that the constructors use arc new cyclic. So when we replace RC with arc, you can see that it is one-to-one conversion. Actually, all the methods look the same. So we now get atomic reference count with the same methods. So code just works. It just works magically. So we just introduced thread safety by essentially doing search and replace. And this is what I did. I did search and replace in this file. All the RCs replaced with arc. All the ref cell replaced with RwLock. That's all my work. And then I had to add a few of those changes like star, write, unwrap. Okay, so those are for the replace. And then read and unwrap, right? So those are the little changes I had to do by hand, but these are big changes. So we got the connection, okay? We got the option arc, perfect. And now that gives us an arc. We do not need to upgrade it anymore because it's already good. So this is already an output. And voila, we shortened the code. I'm happy with this. Now, I wonder if there is a way of doing these two lines of code in one line, saying, I want to exchange the value, okay? Like, for example, I expect that atomic cell has some sort of exchange function which will return the old value and put new value in and do all of it atomically, right? So we might be able to use that then in the episode about atomic cells. Okay, so let's continue with this. Okay, so here we've got the lock of vector of weak references, and yeah, same, the constructor is updated. We have here the connections write, unwrap, push this time. So we just push because we unwrapped and it is a vector of weak pointers. So we lock for writing and then we push. At the same time, the get connections gives us a vector of arcs. So what it does, it reads, it locks for reading. Okay, we lock for reading, and we map this vector into a new vector. We upgrade each connection to an arc, right? And we collect as a vector. So so we get a copy of arcs. So we increment reference count and the pointers to the same pins, right? That's how get connections work. And now other functions are implemented in terms of get connections, so they don't really worry about locking. So when it comes to locking of connections in this implementation, it's very fine-grained, right? You only lock for the moment when you wanna just give me the connection, the current one. If it changes in the meantime, I don't care. I just want a snapshot of what is the connection right now. For example, if I'm asking this pin, give me the connection, I'm gonna get this connection, right? And let's say there is a competing thread that is changing this connection, right? So I have received a weak pointer to this pin, okay? And competing thread has set the connection to be some other pin in some other node. For example, we're processing some nodes and at the same time user has click mouse button, drag the connection to a different node. And this is what happened, right? So we're still having this weak pointer to this, this pin, right? But user has deleted this node as well. And perhaps our next instruction will be saying, get me the node, but it will say, oh, it cannot upgrade the weak reference to the node because node is dead. So, the upgrade will just return, I think it returns option, right? Upgrade returns option, so it will just return none, okay? So yeah, it will just return none, and we will not execute the code that would normally execute in that case. So this gives us some reasonable amount of thread safety, very fine-grained, no deadlocks included, which is pretty good solution, right? And it's probably one of the best solution you can have, and achieved in a very cheap, quick way without really thinking much, right? So we have this thread safety achieved by just replacing RCs with args, ref cells with RwLocks, and suddenly, you know, everything just works perfectly. This code here of example didn't change at all. I didn't change a single thing here, maybe except this types here. I changed them to arg. Okay, so as I said, I did search and replace RC with arg. Bang, works. Search and replace ref cell with RwLock. Bang, it works. And I have a thread safe code in Rust, you know. So yeah, and the reason it's so easy is because Rust will prevent you from modifying updates if you don't have mutable access. Okay, so let's run this to show you that this works. It does work, as we see, same numbers, 200.5, 1600.25. These are the numbers as we remember from calculating those 10 by 20 multiplied and divided, 20 by 80 multiplied and divided. So numbers are correct, right? So this implementation, very quickly done, very safe. The consistency of results in this graph with the changes done dynamically by the user, let's say, if there was any UI to this graph and if these nodes were running in multi-threads, you know, there is some eventual consistency, right? So that's what we can guarantee, an eventual consistency and safety that nothing will blow up into our face, okay? Let's look at the different approach. So remember, previously I said that all the methods were immutable, everything was constant, and I was using ref cell to update the values in nodes and in the pins. So now I changed this. So I call it cleanup, but is it really a cleanup? You know, it's just changing the semantics of all these bits here. So for example, we know that when we do connection on the pin, technically this is a mutating thing on the pin, right? We're changing the pin when we're connecting. So I said, okay, try connect will be a mutable method this time. This connect is also a mutable method because we, you know, changing the pin, but this will have consequences. Now, there is a change here. You see, it's no longer RC of then graph node pin node base. It's not RC, it's RC of ref cell. And as far as I could find, this is the recommended way of having an RC to an object that we can modify. So if you have just RC, I think there is no way of accessing mutable reference to underlying pointer. You have to use something like ref cell to access it. And we will learn very soon that there cannot be any other option, right? All right, so let's see what are the next changes, because there's more changes. So process forwards, process backwards, do those need to be mutable? So I don't know if they need to be mutable given that how things work here, but you know, no, values will change, right? Like we're processing the graph. When we're doing that, the intention is to change things. You know, and you can ask question, is the graph like a pipeline and the water that flows in this pipeline doesn't, you know, concern the pipeline, right? So the pipes are not changing. It is the water that is flowing in the pipes. So the pipes are not changing. So why are we saying that pipes are mutable? So the node graph is like those pipes and the data in the node graph is like this water. But on the other side, here I wanted to try the different approach, saying that we are actually changing the graph when we're changing the data, right? So we say it is mutable, okay? Let's see how that will go, and maybe it will go wrong, or maybe it will go well. There will be consequences of doing that. As I have mentioned earlier, everything is in ref cell now, because if it is in RC, it has to be in a ref cell as well in order for us to be able to change it. Otherwise, we will not be able to call those mutable methods on those pins. So if I wanted to call try connect on any of those pins that I'm gonna list, I have to have a mutable pin, you know, so it has to be in a ref cell. I have no choice. All right, what happens here? So my self-reference to a node in the graph node pin now is in the ref cell, and the reason for that is, well, I'm not going to be changing this reference, but I'm gonna be calling process forwards and backwards, which is a mutable method. Okay, so in order for me to call any mutable methods on any nodes or pins, I have to put nodes and pins into ref cell, because RC is not gonna allow me to do that. So here we go, it's in a ref cell now. But the benefit is that now data is just like this. It's not in a ref cell anymore, okay? So we just moved the ref cell from one place to another place. We can see that the constructor takes weak ref cell in graph node now for the pin. And we can see that this constructor of graph node input pin also, uses this ref cell here. So I have to wrap self into ref cell when I construct it. So that's the change required. But now we have this connect, which is mutable, and it can call connect internal, which is mutable, right? So you can see that the connect internal requires that self is mutable, but it does not require that the output pin is mutable. Why is that? Because we are changing self connection, but we are not changing output, okay? As we said before, connect internal is a single way connection. So it's from self to the other, so we're not changing the other. And in order for us to get a weak reference to the other, because we don't get weak reference here, we have this field me, right? So in C++ we have shared from this, so this me is playing a role of shared from this, right? So why is output pin mutable in the connect method? It's mutable because we also call connect internal on the output pin in this case, so we want to have symmetrical connection in both directions. So we have to modify both pins, okay? So now we have this mutable connect. The get connection is not mutable. So as we said earlier, get connection is in competition with connect, right? Because we might be changing the connection and we might be accessing the connection to just, do the processing, for example. Receive data is mutable because data comes to our pin and we store it in our pin. So see, we set the data of our pin. So that's why we are changing. Get output node is not mutable, okay? We just get the connection. From that connection, which is ref cell, we borrow a reference, right? We cannot modify this reference, but we don't need to. We just want to get the node, right? So we're gonna get the node and return here option RC ref cell of the node. Now, propagate backwards. So that's a mutable method, right? Okay, I think this doesn't need to be mutable. Let's see what that will do. Okay, it doesn't need to be mutable. We're going backwards, so that will not change our value. So we're actually borrowing the node mutably that is attached to the pin connected to us, right? The pin is an output pin and we are the input pin, and the output pin that's connected to us, that one will be changing, right, when we propagate backwards. And we have disconnect. Disconnect has changed as well. It's mutable, and yeah, it's more or less the same thing. It's just mutable now because we're changing. So this is graph node output pin, and then connect is again mutable, and then connect internal will do push, right? So this push itself, as you see, it takes a mutable vector. So previously we were borrowing mutable, now we don't have to be borrowing, right? So by removing connections, as you can see, connections here are no longer in the ref cell, but they store ref cell to pins. So it's like we move the ref cell from one place to another place. This ref cell has to exist somewhere, there has to be some way of protecting this mutability. Right, so here's the changes for the nodes. So the pins are no longer in RC, they're now in RC ref cell as expected. So the interesting thing about borrowing mutable is that now you need to manage it correctly in the functions like, for example, process for backwards and forwards. Yeah, what will happen if I just do here borrow immutably this one? Yeah, I don't know. Let's check if that will explode. Run test. It didn't explode. Oh, okay. Remove this mute. Ah, I know why. Because we don't mutate anymore. Okay, you see, this is the thing. That function is no longer mutating anything. Okay, that was my mistake. I admit to this mistake. So this function doesn't need to be mutable. Just though we optimize that, we reuse the same borrow. Yeah, okay, so let's see transform node. So you can see that we borrow for processing backwards, to propagate backwards. We receive data that requires mutable. We just do like this, borrow mutable. And then input pin, get data, clone, that's fine. We don't need to, now we can borrow, just borrow the pin normally. Yeah, so the only thing we need is this mutable for received data. So we want to make sure that we keep this mutable borrowing as short as possible. Of course, it will split this operations to not be, atomic, but in this case, this is not even multi-threaded, so it's not a problem, Output pin borrow set data. Okay, so you see for set data and for receive, we need to borrow mutably. Everything else is immutably. And here for process forwards, yeah, so self output pin instead. We probably want to do it this way. Yeah, okay, so this is what we did. And now, as you remember, we can copy this into our thread safe code. Just replace it bluntly like this. And then we do replace all borrow mutable with write and unwrap. Just look at this, it's just converting itself on its own. And then borrow immutable, we convert into read. And it would be much easier if RefCell just implemented the same protocol, because we are essentially reading and writing from the RefCell, so why is it not called read and write? Okay, let's see if this change has damage to the code in any way. I think this is all the changes for now. Yeah, let's see if that will work. Does. Okay, let's see if that other one will work. It did. Look at this. So we have a thread safe, two thread safe versions, right? So both of the thread safe versions use immutable node, okay? But they differ in a way that this one is having pins that are mutable, and the other ones kept the pins immutable, but then this lock was on the other side. So if it, instead of putting lock inside the wick, in the other version we have a wick inside of a lock. So that's what the difference. Now you may think, which way is a good way? That's a good question. So in this case, you drop the responsibility of locking it onto the input pin if you're changing the output pin. In the other version, you are locking it in the output pin. I'll show you the difference. This is, for example, pin. Okay, so you can see that in this version, we lock the self. Okay, we say self write, self data write. And in this version, self is mutable and we just assign without locking. So the locking has to happen, but you see the locking happens on the outside. So we have received data. Okay, so we are mutable. Okay, so that's a bad example because someone had to lock us to receive data. So who has locked us? So you can see that when we send the data, so we are the output pin and we are sending the data to some input pin. So we can see that we are the ones who are locking the input pin. So in this solution, locking happens on the outside of the pin. Someone who owns the pin, who knows the pin, someone who wants to use the pin has to lock the pin. And in this solution, the pin will lock itself if you want to use it. So that's the difference between the two solutions. Okay? This is the only difference. The granularity of locking is very much the same, although in this solution, if pin locks itself when you use it, you don't have such a control from the outside what is locked. Okay, so yeah, it works, it's thread safe. But whenever you call like set data in methods like this, you just the lock is hidden from you. This write lock is hidden from you, so you cannot do other mutating operation under the same lock. It will be acquiring a separate lock. So if you wanted to do two operations that would lock the pin, they would not be at the same transaction. You couldn't create a transaction of this. Whereas here in this approach, you can acquire a lock, okay, of this input pin, and then in that lock, you can do connect and receive data in this one lock. So that's a transaction, which means that if it is in one transaction, any competing operation will not interfere in between. It will not, like this connect and receive data, there will be in one, there will be like atomic. Whereas in this version, there will not be atomic. Okay, it will be safe in a way that the connecting will be safe individually, the received data will be safe individually, but if you call one after another, you don't have a way of making them a transaction that goes together. Okay, you cannot make this connect and receive data as a together operation. So yeah, also, let's say you have a node with 2 pins and you want to lock 2 pins, okay, at the same time. You want to make sure that you locked all the pins when you're receiving data. So in this version, you cannot do that because each pin will lock itself when you call receive data. Whereas in this version, you can first acquire all the locks, see if you are successful acquiring those locks, and then you're going to receive data on each of those pins. So maybe you have data on the pins that is dependent on each other in a way, some way, and you want to make sure that data that is on one pin is not going to be like out of sync with the data on the other pin for some reason. So you see, there is some kind of use case, right? There is some kind of use case when you would like to lock all the inputs before you receive from them, right? So the S6A is an option that gives you ability to do transactions. S6B is kind of self-contained synchronization. So these two versions are kind of opposite to each other in a way that this one, which has lock inside of the weak pointer, okay, allows you to do transactions, okay, whereas this one, which has a weak pointer inside of a lock, is self-containing the locking. So in this version, when you do operations like connect, or you can see here connection write, okay, or receive data, okay, set data, those operations do locking internally. So when you call the method, the method itself will do the lock of data required to be locked. In this case, when we have weak reference, when we have weak RC of locks, right, then it is the user that locks, okay? In this case, it is the self that will be mutated, and the user has to lock us, okay? So this one might be more beneficial in general, because you can create transactions, right? But you need to do locking from the outside. So case for locking on the outside. So you have this transform node here. So in here you can see that we have to do the read lock to propagate backwards on the input pin. So that will go to the input pin of our transform node and tell this input pin, hey, who is connected to you? Tell them to process, okay? And that is read only for the pin. We're not changing the pin. The next thing is to make the pin writable, so we acquire the write lock, okay? And when we do that, we put the new data into the pin, okay? And then we make the pin read-only, and we get the data from this input pin, okay? So, you know, we don't support here upgradable lock, unfortunately, in the sync library. RwLock from sync library doesn't support upgradable lock. Upgradable lock would make it just one lock here, and this will be the upgrade here. And here we would downgrade if possible. But we don't have this option. So we have 3 granular separate individual locks going on here. And if there is granularity, then some other thread might be doing to those pins something here and something here. Okay, so the data that we received here might be some x1, but the data that we're getting here might be some x2 because some other thread has changed it. So we could avoid that by retaining this write lock and getting the data under this write lock instead. Pin write. Okay, let's put that in here. Because it wants to be mutable. And then here we want to just reuse this lock. Okay. Can do that. So when we do that, we're creating a transaction now. A transaction in which we receive data, and here we're getting the data that we received. So we guarantee that no one has changed the data between our receive and get data, okay? So that could actually be wrapped into, like, this received data could actually return the data and problem would be solved. Maybe that's the way to fix the problem. It sounds like, you know, this is the solution. Make receive data, return the data. This was thread safety discussion in Rust. And only Rust. Why not C++? We're going to look into C++ multi-threading in the next episode because that's probably going to be a long talk and it requires a long discussion. Okie dokie. So see you in the next episode. Bye.